Hi, everyone. Welcome to the Virtual Night Sky version, April 21st, 2021. Today, I think you might already know that we're really celebrating Earth Day, which is really tomorrow, but our program is on Wednesday nights, and we'll give you some announcements of some things that are going on tomorrow if you want to tune into some Earth Day events as well. The School of Earth and Space Exploration, as its name implies, is both earth sciences and space sciences. This is actually not that normal. Usually, astrophysics and astronomers are attached to a department of physics at their universities. That's true around the world and for almost 300 years. ASU decided about, I don't know, 12, 14 years ago to actually combine our geologists and our astronomers and put them in one school. School of Earth and Space Exploration. Uh, that's where I work. My name is Rick Alling, and I run the Marston Exploration Theater, the room behind me in this scene. During COVID, we have been using this opportunity to actually do what we call virtual night skies. And generally, those themes are about astronomy, about the night sky, about themes to look at in space. And we'll get back to that in a couple weeks. But we also thought we would take this moment to invite a geology professor, Steve Semken, and we will talk about tonight. We're going to kind of examine Arizona geology, things that you can see when you drive back and forth across the state. If you go visit northern Arizona, you'll learn tonight, about kind of what makes it work and what is the geological underpinnings of the landscape in northern Arizona, southern Arizona, and all around. So we'll get to that in just a moment. I wanted to introduce the team that's with me. My colleague is Meg Hufford. She's always with us on these programs, and she and I are involved in touring and inviting people to ASU for experiences at the School of Earth and Space Exploration. And of course, during COVID, we're not there, and so we're engaging you this way instead. Kim Baptista is on the line. And she's your webmaster tonight. She puts the webinars together, handles the communications, and keeps us in line, and kind of like takes care of the production parts of the program. And we are, of course, indebted to her for that. I've got four students tonight. Alicia Hyatt, you've seen before, and you'll see her later in the program to give you a little update about a little helicopter on Mars. We'll see that. Justin Baez is going to give a presentation tonight in a focus we call resources. And tonight you're going to learn about Google Earth as a resource. And Justin's going to show you how you can learn a little bit about geology, world geology, by just sort of focusing on Google Earth a little bit and using it as a tool to examine the Earth. And two other students, Alex Blanche and Spurti Kachere, are actually here. They will be helping in the background, answering questions and whatnot. I have some housekeeping things going on here. So we do not have chat, but we do like to engage you with questions. So you can go to the little Q&A button on the bottom of your screen. And if you want to, just ask a question along the way. We will either get to it while the program is going, the students will monitor and do that, or we will try to save a handful of questions for Steve at the end of his talk about geology. And but in any case, usually we get to all of those questions, and we do like to hear from you. And if you are a school-age student, K-12 or whatever, don't give us your last name, but if you don't mind saying first name and grade level you're in, produce a question that way, I think that would be really good. We'd like to hear from you. We'd like to know what grade you're in, and what school, and what age you are in school. The other thing is we do live transcriptions, and so you'll see if on your screen my voice is being written across the bottom of the screen. We do that on purpose because it's our ability to sort of like capture these and do live transcripts after the fact, so we can rebroadcast. If you don't want it, you can turn it off. So there is a closed caption button at the bottom of your screen. It says CC, and under that it says live transcript. And if you want to, you can just turn it off and mute it for yourself if you'd like to. So all of those things are on your own. We usually advise people to use a little button up at the top right corner. It says fit to screen. That'll give you a full view of everything that's going on. and that will be how we work that. After all of that is over, we'll break for some question and answers. We'll have some poll questions. I'll give you some updates on what we're going to do in future weeks. And I hope very much hope you're going to enjoy this show and celebrating Earth Day. So without any further ado, our guest tonight is a professor at Arizona State University, Dr. Steve Semken. Steve used to be our boss a while ago. ASU takes very seriously our outreach program, and Steve was an associate director of outreach for us for about 3 years. And he knows an awful lot about Arizona. He teaches a lot in the environments of Arizona and around. He'll tell you a little bit more about himself, but I'm not going to go on any farther. I'm just going to introduce you to Steve and have him talk to us a little bit about Arizona geology. Welcome, Steve.
Thank you, Rick. And thanks everybody for joining us today. I'd like to say happy Earth Day Eve and happy Earth Week, happy Earth Month. Of course, I am a geologist, and we geologists always like to say that to us, every day is Earth Day. We think about the Earth all the time. It is our livelihood, but it's also our passion. And as you can see, I've got a picture of Grand Canyon behind me. I wish I was actually broadcasting from Grand Canyon. I'm broadcasting from Tempe. But Grand Canyon is a place that I know very well. I've done a great deal of work there, and happens to be one of my favorite places in the known universe. And the fact that we in Arizona live in the Grand Canyon state, we can take some pride in having this magnificent, one-of-a-kind geological landscape right in our backyards. So I'm going to go ahead now and share my screen so I can show my presentation. So I'm going to talk for a little while about a topic which is very important, I think. We have spent the last year with these wonderful virtual night sky activities talking about looking up at the sky and seeing what we can observe and what we can learn about the solar system and the universe from our observations. And that's wonderful and very important. But tonight I'm going to talk about looking down, or in some cases looking up if you're down at the bottom of, say, Grand Canyon, to look at the materials of the solid Earth, the Earth's crust, or the rocks, of course. So, this title has two meanings, of course, because Arizona most definitely rocks, but Arizona also has rocks. And so, starting with this picture here, this is a photograph I took from down at the bottom of Grand Canyon. I was on a raft floating on the Colorado River, which is a great experience. I hope all of you have a chance to do that at some point. And looking up all the way up to the rim of the Grand Canyon. And what I'm seeing in this picture here are rocks that vary in age, from the oldest ones down at the very bottom of the canyon here, the black ones. Those are almost 2 billion years old. They're about 1.7 billion or 1,700 million years old. And then they get younger and younger as they go up. And because that's one of the sort of principles of geology, is that the higher up you go in a stack of rocks, typically the younger they get. And Grand Canyon is special because it carves through such a magnificent stack of rocks. And I'm going to bring you back to Grand Canyon in just a moment. But first, I want to talk a little bit about rock. Rock is the solid mineral matter of planets, okay, terrestrial planets. And rock and metal together make up the bulk of Earth, but also the other inner planets, which we sometimes call the terrestrial planets. The word terrestrial means Earth-like. And we also think of them as rocky worlds. And this is a nice little diagram that I got off the web from NASA that shows the terrestrial planets from Mercury to Venus to Earth to Mars, and our own moon, which is large enough in comparison to Earth that we might even think of it as another terrestrial planet, and the interiors. And all of these worlds basically have three main components to their interiors. At the very, very heart of each of the planets is a core. In some planets like Venus and Earth, we have sort of a distinct inner core and outer core. And that core is made of metal, right? The reason why the metal is there is the metal is heavier, it's denser than anything else that the planet is made of, and gravity's kind of pulled it all to the bottom. Above that, though, is a very, very thick layer, which we call the mantle. And the mantle is made of rock. It's made of rock that's fairly heavy or fairly high density. And then the very outside of the terrestrial planets at different thicknesses, we have the crust. And the crust on Earth is what we live on. The crust is what makes up the floor of the oceans and makes up the continents. And so we live and we earn our livelihoods, and we travel on the Earth's crust. And actually have a few samples I'd like to show you. So over here, This is an iron nickel meteorite. This fell down in Siberia. Okay, this is an extraterrestrial object. It doesn't come from the Earth itself, but it's a big lump of metal alloy. It's a big lump of iron and nickel. So it's a pretty good stand-in for the Earth's core. This is what we think roughly what the Earth's core is made out of. The innermost part of the Earth's core is solid, and then the outermost part of the core is liquid. It's hot molten metal. You can imagine that. The interior of the Earth, the temperature in the interior of the Earth is not that far off from the temperature in the surface of the sun. So give you some idea of how hot it is down there. Not exactly, but it's pretty close. I want to point out too, this camera I have, you can see on the right there, you can see there's a scale. So you can see the size of these rock samples when I bring them out here. And I apologize because I realized that the writing is backwards. I have this document camera that plugs into my desktop computer with a USB connection, and for some reason it's not able to turn it around. So please forgive the backwards writing, but the length of the lines is still the same. So each one of these little white and dark bars is 1 inch, and these are centimeters. So you get a pretty good idea. So the core is at the very interior of the Earth. The next layer out from the core is the Earth's mantle. And this is a pretty good stand-in for the mantle. This is a rock that's called peridotite. And the peridote in peridotite is peridot, which is a green mineral. The technical name for it is olivine. Those of you who have birthdays in August, and I'll shout out to my daughter who has a birthday in August, that's your birthstone, green peridot. But it's a mineral that contains iron and magnesium and silicon, and it's actually makes up the great bulk of the Earth. So the Earth's mantle, the layer that's just above the core, is made out of this rock, we think. Now, when you get to the crust is actually pretty thin. If we can think of the Earth as a peach is a pretty good analogy for the Earth. The core is like the pit of the peach. The mantle is like the flesh of the peach that you eat. And then the crust is the skin of the peach, except that the Earth's crust proportionally is even thinner on the planet than the skin of a peach is on a peach. It's remarkably thin, but it's the most important part of the Earth to us because it's what we live on. It's what we get our soil from. It's what we get our minerals from. It's what we get our water from. So the Earth's crust, even though it's just a tiny little bit of the Earth by mass and by size, it's really important. And these two rocks are pretty good stand-ins for what the crust is made of. What's special about the crust is that the crust of the continents, like North America, South America, where we're living, is different from the crust of the ocean floor. The ocean basins, the oceans are deep, and the crust of the oceans is thinner and it's deeper. It rides lower on the Earth's mantle. And this rock up here, this black rock, is called basalt. It's a rock that is made, again, contains iron and magnesium and silicon, a little bit of aluminum and other elements. And this is pretty much what the crust of the Earth underlying on top of the oceans looks like. This rock down here is granite. Granite is a rock that has certain chemical compounds in it that we call minerals. And it contains, compared to the basalt, it contains a lot less iron and magnesium, and it contains more silicon, more aluminum, more calcium and sodium and potassium. And actually a potassium-bearing mineral substance in there is what gives this rock its beautiful pink color. And this is what the continental crust is like, basically. It's the average, if you think of the average composition of the continental crust, it's like a granite. So these 4 rock specimens are kind of really good stand-ins for the Earth as a whole, okay, and the terrestrial planets as well. We probably don't have a lot of granite on the other planets, but there's a lot of basalt. The rock that makes up the ocean floor is actually the most common rock in the terrestrial planets. So there's certainly that, and then the metal in the core. So you may remember this from basic science classes you might have had, that the interior of the Earth is layered as you go down, that it's not all mixed up. All of these different materials are separated into these layers. And again, you can see the core, the iron and nickel metal we just looked at. There's the solid inner core, the liquid outer core, then the mantle. And you see the mantle by volume is the biggest part of the Earth. It's much thicker than the core and certainly much thicker than the crust. And geologists sometimes talk about the lower and upper mantle. There's slightly different types of rock in those. But in general, the mantle is made of that dense green peridotite that you were just looking at a moment ago. And then the crust at the lower density rock is here. And this cross section here shows you the relationship between the continental crust and the oceanic crust. The crust under the oceans is very thin by comparison. The crust under the continents is much thicker. This is the rock that's like granite, and this is the rock that's like basalt. Now, the uppermost part of the layer, the entire crust plus about 10% of the mantle that's directly under it, is rigid and brittle. It's solid. It doesn't flow. It actually just can actually break, and it's kind of like a stiff shell on the outside of the Earth, which we call the lithosphere. It's a rigid and brittle shell on the outside, but below that, below that, the mantle that's just below it is actually able to flow. It's not liquid. Okay, there's actually the only really liquid part of the Earth's interior is the outer core. Most of the Earth, the rest of the Earth is pretty much all solid, but it's actually plastic. It's kind of like chewing gum compared to, if you sort of compare chewing gum in the refrigerator, how brittle it is, that would be the lithosphere. And then if you put chewing gum on the dashboard on a hot Phoenix day and it got kind of soft and kind of flowed, that would be this part, which we call the asthenosphere. And I wanted to mention that because those brittle outermost layers, that lithosphere, actually doesn't just sit there. The outermost solid layers of Earth, our geologic evidence is that they're broken up into pieces that we call plates. And those plates are not stable. They're not static. They're actually moving across the surface because the flow of the asthenosphere, the soft stuff that can flow directly below them, is basically pushing them around. And so the lithosphere, pieces of the lithosphere, we call them plates, they interact with each other. They bump into each other. In some places, one plate, which makes up the ocean floor, will plunge down beneath another plate, which makes up the continents. In some places in the middle of the oceans, we have what are called mid-ocean ridges, where the two new plates are being formed and they pull apart. And this model, this basically explains how the Earth works. And what this tells us is that the outermost part of the Earth is actually very dynamic. It's constantly in motion. Now it's moving at rates that aren't really that easy to see. The rate at which the plates move around is about the same speed at which your fingernails grow. Okay, so if you were to just let your fingernails grow for an entire year, maybe it would be growing anywhere from like a few millimeters to maybe, half an inch, maybe an inch, depending on how much gelatin is in your diet, maybe. But that's about how fast the plates move. So it's pretty slow. But over long periods of time, millions of years, those interactions have consequences. And that's what we call plate tectonics. And so the crust of the Earth, unlike the crust that we think on some of the other terrestrial planets, the crust of the Earth is really changing all the time. It's constantly being shaped from below using these processes of plate tectonics, processes of the interior of the Earth. And we have a technical term for that. We call those geodynamic processes. These are the processes that bring continents together. They lift up mountains, they create volcanoes, and they make earthquakes. These are the kind of processes that we see that are triggered from the heat on the interior of the Earth. But the Earth also has an atmosphere. It has water and it has air, has a hydrosphere, and that liquid water and that air are flowing across the surface, and they act as a sort of a counter to the internal processes. These external processes are constantly wearing away at the Earth's surface and wearing things down, grinding away at the rocks of the crust, turning them into loose materials that we call sediments, like sand and gravel and mud, and then carrying those sediments down to the lowest part on the Earth, which happens to be the ocean floors. So those processes are happening on the outer part of the Earth, and so we would call those external processes. The technical term is geomorphic, and that really means Earth's form. Geomorphic is Earth's form, and geodynamic is Earth's dynamics, Earth's power, essentially. And what makes the internal processes go is the heat of the interior of the Earth. It's like a source of energy that keeps those processes driving. What drives the external processes is the heat of the sun. We're being constantly bathed in solar energy, and solar energy causes water to evaporate. It causes air to move from one place to another because you have differences in temperature and differences in pressure. And so because of that, as we say here, the crust of the Earth is constantly shaped from below and sculpted from above. And here we are, we're kind of standing in the middle, right? We're kind of at the surface here. Some scientists call that the critical zone, sort of the first few meters of the Earth's crust and some short distance above it. And we're basically in between these two sets of processes are kind of acting above us and below us. The significance of rocks is that those processes, those changes to the crust leave behind a record of what they've done. And the record is not written in books, but it's written in rocks. So rocks are literally a record of the processes that have shaped the earth through time. So rocks enable us to read the narrative of the history of the earth. We like to think of Earth's history as being like a story that's been going on for billions of years. And what geologists do is we have learned to read that story in rocks. And how do we study rocks? Well, we study rocks in the field. We look at rocks and structures in the landscape. And that photo was actually a bunch of Arizona State geology students learning how to map rocks and how to study rocks in the field. And that's out near Superior, Arizona, where they're working. We collect physical evidence. We collect rock samples. We collect crystals. We collect fossils. Fossils are traces of former life that are present in rock. But we can also look at rocks from a distance. We can look at them from satellites. We do remote sensing. We can collect pictures of structures. We can see structure of the crust sort of at larger scale from a greater distance. And we can analyze the specimens we collect. We bring them into the laboratory and we measure different properties of those materials, like what they're made of and maybe how old they are. We can use a radioactive dating to measure the ages of the rocks. So we interrogate rocks in lots of different ways. And I kind of wanted to show you a couple things. Pretty much anytime you see a geologist going out in the field, they've always got one of these things on them, right? This is just a 10 power magnifying lens, and it's on a lanyard. We usually wear them on that. We like these fancy lanyards, and we carry them around our neck because we use them to look at rocks. Some of the features in rocks are big enough that you can see them with the naked eye, but some of them are not. And so the 10 power hand lens allows us to zoom in on some of those interesting features, different crystals or different ways that the crystals are oriented. And then you'll also see geologists carrying rock hammers into the field. You know, so well, that seems rather destructive maybe, but the fact is that the surfaces of rocks, when they're exposed to the elements, they tend to change. They get coatings on them, which actually conceal the true nature of the rock. So geologists, we carry these hammers so that we can take a piece of rock and we can break off a small piece of it and look at the inside, because the inside surface of the rock is actually more telling for what the rock is really made of, or what it really looks like. So you'll always see a geologist in the field. We have lots of different tools, but probably the two most common field tools for looking at rocks you see right there, the hand lens and the rock hammer. And certainly when you see me in the field, I'll always be carrying both of those, and our students will as well. So we interrogate rocks. So now let's get a little bit more into detail on rocks. There are thousands and thousands of different kinds of rocks on the earth. And if we just sort of looked at every rock individually, it would be way too complicated for us to make any sense. But luckily, all of those rocks tend to fall into one of three basic categories. And again, these are terms that you may be familiar with. You may have heard this before. Geologists recognize three basic types of rock: igneous, sedimentary, and metamorphic. And the word igneous, that comes from the same root as the word ignite, which of course means to light something on fire. And the igneous rocks are the rocks that came from molten rock, from magma down in the Earth's interior. When rocks get hot enough to melt, that magma, molten rock, moves up through the crust, and it may solidify inside the crust, or it more pour out onto the surface in a volcano. And when it pours out onto the surface, we call it lava. And the rocks that form when that magma or that lava cools enough to get solid again, those are igneous rocks. But remember, we talked about how we have these processes that are grinding away at the surface. And so igneous rocks, when they get exposed to the surface, they're eventually going to get ground down by wind and ice and water, and they're going to be pulverized into tiny little pieces that we call sediments. And that's the loose material at the surface: sand, mud, gravel, salts in some cases. And we call those sediments. And the word sediment literally means to settle. And that's because these things are settling on the surface. So sediments get buried and they pile up, and they can be turned into rock too, and they become sedimentary rocks. So these are the rocks that form at the surface. And then metamorphic rocks, that's the third type. The word meta means to change, and the word morph means form. So these are rocks that change form. And these are rocks that get subjected to high pressure and high temperature at the depths in the crust, and they change without melting. They will change form, but they will stay solid. So they'll assume a different kind of structure and composition, they'll become different rocks. And what's really significant, why we care, why we're interested in these three categories is very simple. Each one of these types of rock tells us a unique story about a different part of the earth. Depending on what part of the earth we are interested in, we look at igneous rocks or sedimentary rocks or metamorphic rocks, or we may end up looking at all three at some point or another. So I want to show you a few examples of each type of rock, okay? So first, let's look at some igneous rocks. We already looked at a couple of them because basalt and granite are two classic igneous rocks. Granite is what you get when magma flows up through the crust but doesn't make it all the way to the top of the crust. It stops in the crust. So that's what you see over here. It ponds in these little bodies and it cools down, but it cools slowly enough that you can get big crystals, big minerals that form in that rock. And these crystals, the dark crystal is called biotite. It's a black mica. It forms little sheets. The pink stuff is potassium feldspar, and the sort of the glassy stuff you can see here is quartz. So this is an igneous rock. On the other hand, if lava pours out onto the surface, typically it cools a lot faster and you get tinier crystals. And that's why basalt looks like this. You can't really see crystals with the naked eye. That's why we bring in the hand lens or even a microscope. When we look at it under the hand lens, we can actually start to see some crystals. But the other thing that's cool about the basalt is you see all these little holes in there. Those were gas bubbles. When that lava poured out onto the surface, it had gases dissolved in it, which was like water and some carbon dioxide and maybe some sulfur dioxide. And those formed little bubbles in the lava. And then when the lava cooled to form rock, the bubbles remained. The gases went away, but the bubbles stayed there. And so these bubbles tell us that this was lava that flowed out onto the surface. So those are examples of igneous rock. Let's look at just a couple of sedimentary rocks. So one of the more common sedimentary rocks on the Earth's crust is sandstone, which is just a rock made of sand that's cemented together. And this is red sandstone from northern Arizona. This is called the Navajo sandstone. And these are just a bunch of red sand grains. So sand grains are made of quartz, the mineral quartz, but they've got a tiny little bit of iron oxide, which is called hematite, and it's basically rust. So you know when metal rusts, it gets kind of that reddish coat on it. This is the same stuff. It's a tiny little percentage, maybe less than 1% of iron oxide that colors the rock red. And of course, you know, in Arizona, we have magnificent exposures of red sandstone all over the place in places like Sedona and Canyon de Chelly and Monument Valley and even in Grand Canyon. Sometimes you can get a sediment that's made out of bigger pieces of sediment. So sandstone is made out of tiny little bits, but by comparison, this is called conglomerate. And conglomerate is a sedimentary rock that's made up of pebbles cemented together. So you got a bunch of these big chunks, right? So you can see some of these pebbles are close to an inch in diameter. And if you think about where this might have come from, well, if you walk around out in nature, where are you typically going to find a bunch of pebbles in one place? The answer is a stream bed. So what this conglomerate is probably an ancient stream bed that got turned into rock. This is a bunch of pebbles that were accumulated in the bed of an old stream many millions of years ago. They got buried and they got turned into rock. So those are examples of sedimentary rock. I'm going to show you just a couple of really cool metamorphic rocks now. This is one of the coolest ones. This is called gneiss, G-N-E-I-S-S. And what's special about metamorphic rocks is because they get squeezed at such high pressure and they get heated to such high temperatures that the minerals in the rock can actually kind of flow. They can actually move around. They don't melt, they don't turn into liquid, but they flow. So this gneiss, you can see these bands of different crystals, and the bands are actually bent in some places. I mean, just imagine, this is a hard rock. Okay, so just imagine the pressures and temperatures that this rock must have undergone to be able to flow and to bend like that. So this tells us that this rock underwent some really intense pressure and temperature, which is probably it encountered at the bottom of a mountain, probably when a mountain was being formed, a large mountain range. Just imagine the rocks that are down deep inside those mountains, what kind of temperature and pressure they're getting, and that's what they're going to turn into. This is another metamorphic rock, which is kind of cool. It's called the schist. See how shiny it is? That's from mica. They're crystals of the mineral mica, which has sort of a glassy look to it. And like the gneiss, the mineral grains are all kind of lined up together in parallel surfaces. But unlike the gneiss, instead of in the gneiss, they form bands. They actually form bands. In the schist, they just form these tiny little layers, almost like phyllo dough. Like if you like baklava, it's a really nice sweet dessert. And you got all those little phyllo layers in there. This is kind of like the rock equivalent of that. And this is called a schist. So these are examples. This is kind of what igneous, sedimentary, and metamorphic rocks look like. And of course, there are many, many other different varieties, but these tell us history of different parts of the earth. Okay, so what I want to do for the rest of the time now, just for a couple of minutes, is talk about one place in particular. But I want to start with this map. This is what's called a geologic map of Arizona. And you can see the outline of the state. You can see where Phoenix is over here. There's Tucson, there's Flagstaff. The dark lines are the main interstate highways, I-40, I-17, I-10, and so on. But each one of those colors represents a different type of rock. And what this shows us is that depending on where you go in Arizona, at the surface, you encounter different kinds of rock. Okay, so the reds and oranges are igneous rocks. Those are lavas. Those are basalts and other things that are associated with volcanic eruptions. The purple here in the middle here, that's granite. So these are actually those pink rocks that were formed deep in the crust, and then they were exposed later on by uplift and erosion. The blues, the different shades of blue, those are sedimentary rocks. And the yellow is actually not rock at all. The yellow is loose sediments. It's sand and gravel. And that's because in southern Arizona, we have all of these desert valleys in between mountains that are covered with sand and gravel. Phoenix itself, if you just walk around the Valley of the Sun, you've got mountains on all sides of you. And those mountains are made out of solid rock, but the valley itself is filled with sand and gravel that worn down from those mountains. So we're gonna look very quickly, because I could easily spend days in Grand Canyon talking about it, but we're gonna look at Grand Canyon because what's special about Grand Canyon is all of the different types of rock are exposed in Grand Canyon, a myriad of rocks. So if you look inside the canyon from the rim, you see different kinds of rocks. If you look at the very, very bottom of the canyon, you see metamorphic and igneous rocks. If you look at the top of the canyon up to the rim, you see all of these layers that are horizontal and kind of stacked one on top of another. Those are sedimentary rocks. And then in some parts of the canyon, you can see sedimentary rocks and a few igneous rocks that, rather than being flat lying, they're actually tilted. And each one of them tells a different story about Arizona. And I want to do a little shout out to something that we created with funding from the National Science Foundation, and this is called the Trail of Time. The Trail of Time, maybe some people have seen it. It's a user-guided geological field trip along the south rim of Grand Canyon. If you go up to Grand Canyon, the trail starts at Yavapai Point, where there's a wonderful geology museum, and it goes west to Grand Canyon Village, where you can stop and have lunch at the El Tovar or the Bright Angel Cafe, and then it continues on to Maricopa Point. It's 4.5 kilometers altogether, and it's basically a walking timeline. What it has is it has all of these wonderful signs that tell the story of Grand Canyon geology. It has samples of every single kind of rock that's found in Grand Canyon, and there are about 40 different types altogether. And then it has these little time markers that you walk along, and each one of these time markers is separated by 1 meter. You can see the two of them in the sidewalk here, and every meter represents 1 million years. Now, the age of the oldest rocks in Grand Canyon is about almost 2 billion years. So it's about 1,700 million years, which means it takes about 2,000 meters to get to the end of the Trail of Time that talks about the history of Grand Canyon, which is a little bit of a walk. You actually sort of physically feel the depths of geologic time when you walk the Trail of Time. Now, we can't all be there. I wish we could be there right now, but I borrowed a few of the teaching elements from the Trail of Time to sort of finish this story by talking about the geology of Grand Canyon. And if you learn nothing else from this talk, what I'd like you to remember is that Grand Canyon itself is geologically very young. It's only a few million years old, which is very, very young by geological standards, but the rocks it cuts into are geologically ancient. They go back billions of years. So the rocks were there for a long time before the canyon was. And looking at that picture again, we have the metamorphic and igneous rocks down at the bottom. We have several groups of tilted sedimentary and igneous rocks, and then a whole bunch of flat-lying sedimentary rocks. and then a few volcanoes at the top, which also give us igneous rocks. And in general, as I mentioned earlier, the stuff at the bottom is the oldest and the stuff at the top is the youngest. So we'll start with the metamorphic and igneous rocks. All right, so looking down, this is what we call the inner gorge of Grand Canyon. This is what you see if you're down at river level. These are the oldest rocks of Arizona. They're the oldest rocks in Grand Canyon, and they're also some of the oldest rocks in Arizona. Two types, the metamorphic rock, the schist, like we saw earlier, and the granite, the igneous rock. They make up the oldest part of the crust. And I actually have samples of both of these rocks. So I'll show you a quick look. Here is the schist. This is the gray stuff that you see in the picture on the left. It's shiny because, again, it has crystals of mica. This is a metamorphic rock, and we can tell because it has those lined up crystals. They're all kind of parallel. And this is the granite. And this is a granite that has particularly large crystals in it. And this is very typical of the granite that's down at the bottom of the Grand Canyon. So we have metamorphic rocks and igneous rocks. And what story do they tell us? Well, they tell us the story of the formation of the oldest crust of Arizona that happened more than 1,750 million years ago, when plate tectonics took a lot of tiny little pieces of crust, like island chains and small pieces of continents, and gradually brought them all together in like this long chain collision. Okay, if you can imagine, it's maybe not the most pleasant analogy, but imagine a collision where people just kind of keep bumping into each. Think about bumper cars. Maybe that's a better one. If you've ever taken the bumper cars, you play it at a carnival. You play with the bumper cars, and you'll be riding in your car, and then someone else will bump into you, and then someone else will bump into them, and you'll have this fun sort of little collision. That's what the Earth did. It took all of these smaller chunks of crust and brought them together. And so this is a map that indicates what we think Arizona looked like at that time. There's the outline of present-day Arizona. Notice that half of Arizona hadn't even formed yet. Only the northern part where Grand Canyon is, but the southern part was still being formed. These smaller land masses were gradually bumping up against the edge of the continent and literally growing the crust outward. And so Arizona, starting at the Grand Canyon area and moving out farther and farther, grew by sequential assembly from all of these smaller land masses being added. So that's what those rocks at the bottom of Grand Canyon tell us. They tell us about the very origin of Arizona. So now we'll look at the sedimentary and igneous rocks that are a little bit higher up. And what's special about them is that they're not flat, they're tilted. And when we go down to the bottom of Grand Canyon and look at them, they are tilted. They're actually tilting away from us in this picture. Not only that, there's a bunch of sedimentary rocks, but there's also places where igneous rocks have kind of squeezed through them. Lava, magma actually, kind of made its way through the layers of sedimentary rock, and we call that intrusion. Literally, the magma actually squeezed its way into the mudstone. And so I actually have pieces of those rocks too, right? So we have this red mudstone. This is literally a rock that was made out of solidified mud. And then this is the basalt. This is the black igneous rock that kind of made its way through. There was a crack in the mudstone, and the magma just kind of flowed its way through there, and then it solidified. And this particular location is very famous for a lot of geologists. It's a place where this picture of this igneous body cutting through the red mudstone is probably in just about every introductory geology textbook that's ever been written. It's really a classic locality. I had the good fortune in 2013 to actually be riding on the river and actually ride right past it. So what these tell us is that this was a time later on in Arizona's history when the crust was being broken open into these big valleys or basins. And those basins were filling in with mud and sand and occasionally some lava. And that's what gave us these rocks. So this was a time when Arizona's crust was being moved around after it already had been assembled. Now it was essentially being pulled apart again as plate tectonics sort of did its work. And then on top of all of those are these flat-lying sedimentary rocks. And when you look into Grand Canyon, that's the part that you usually see the most readily. These are the big, thick layers of rocks that pile up on top of everything. And you can see beds that are red and beds that are white and different thicknesses. And some of them are kind of sloping and some of them are kind of vertical. And these are all flat-lying beds of sedimentary rock. And they're distinguished by what they're made out of. So There's limestone, which is made out of calcium carbonate, the same stuff that's in Tums and Rolaids. And then there's sandstone and mudstone. And I'm going to show you a few of these pieces of sedimentary rock. So let's go ahead and bring out that document camera again. So this is the limestone. Limestone is deposited on the seafloor. So this is a rock that came out of basically when seas were flowing over the surface of Arizona, which we'll talk about in just a moment. This is the sandstone, kind of a reddish white sandstone, and it has bands in it because there's little bits of iron oxide that kind of water passed through there and kind of carried it through there like a paintbrush and actually kind of colored that rock. And so this is the kind of stuff you see, and it's just piled up to great heights in the interior of Grand Canyon. And what does this tell us? Well, this tells us something kind of a cool story. This tells us that after all that other stuff that was happening, we're moving ahead now to about 515 million years ago. Much of Arizona was actually pretty flat lying. It was pretty low in elevation. It was pretty flat. And when the sea levels rose, the sea levels occasionally would rise and they would fall, and they would rise. Each time the seas rose, they would flood over the edge of Arizona and they would leave behind deposits of limestone. But the beaches, sort of at the edge of the seas coming in, would give us mudstone and sandstone. And how do we know that the seas were there? Besides the fact that the limestone was there, we have a little bit of other evidence too, in the form of fossils. Okay, so this is a trilobite. This is a little marine invertebrate that lived on the sea floor at that time. Trilobite literally means three lobes. You can see it has a three-lobed body, kind of like a little beetle almost. That's crawling around on the seafloor. It's one of the earliest forms of animal life that lived on the planet, but it lived under the seas. And then we also have corals. This is actually a piece of fossilized coral. Not quite the same as what makes up modern coral reefs, but each one of these little animals made its own little tubes for its home. Okay, so you can actually see tubes. These are fossil corals, and these are present in the rocks, and they look kind of like spaghetti, don't they? And these are fossilized marine organisms, about 500 million years old. And then here's one that's kind of cool. This is a fossil seashell. This is called a brachiopod. You can see it's kind of got a shape like that. That's a seashell, and that one's only about 300 million years old. That's sort of to the end of the story. But the fact that we don't always have limestone tells us that sometimes when the sea wasn't there, instead it was kind of dry, and Arizona occasionally had great deserts, and the deserts are what gave us the sandstone, because the sandstone is literally these fossilized sand dunes. These are like ancient sand dunes that occupied Arizona at different times in its history. But again, the sedimentary rocks tell us the story of these ancient dunes that occupied the Arizona's surface at that time. So the story that's being told here is that Arizona was pretty low in elevation, was down close to sea level for a long time, and it would occasionally be underwater and it would occasionally be dry, and that would be underwater again, then it'd be dry. And so we end up with these alternating layers of limestone and sandstone and mudstone and limestone and sandstone and mudstone. But the big question is, how did they get to where they are today? Because this stuff was happening. Arizona must have been pretty low in elevation, but today the rim of the Grand Canyon is more than a mile high. Okay, the rim of the Grand Canyon in some places is as high as 8,000 feet. How did it get up there? Well, the answer was that not long geologically after those depositional events where the sediments were being put down, the entire Southwest was uplifted. Plate tectonics took over again and hoisted the entire Grand Canyon area up, as well as all of northern Arizona and even southern Arizona at that time, high above sea level. And that allowed the Colorado River to start to cut through those rocks and carve out the Grand Canyon. So without the uplift of the entire region where Grand Canyon is, we wouldn't have a Grand Canyon today. Now, the question a lot of people ask is, are there any dinosaur fossils at Grand Canyon? And the answer is no, because the rocks that contained the fossils were on top of the rocks that are still there today, but they were all stripped away. There are actually a whole bunch of rocks that were there early on, but then when the plateau, when the region where the Grand Canyon is was uplifted, the youngest layers, the layers at the top, including all the layers that had the dinosaur fossils, they got stripped away. So you go to Grand Canyon, you don't find any dinosaur fossils, but you don't have to travel far. You could go north of Grand Canyon up into Utah, or you can go east of Grand Canyon into far eastern Arizona, New Mexico, and Colorado, and you will find dinosaur fossils because those rocks that have been stripped away from Grand Canyon are still there. And so even though you don't see dinosaurs at Grand Canyon, I wouldn't want to leave you without looking at least one dinosaur fossil, okay? And this is a dinosaur track. Now, can you see it? It's a little hard to tell, but if you look, you can see 3 toes. There's one toe, there's another toe, and there's another toe. And the size of that, that's a footprint that one of the earliest dinosaurs left behind in northern Arizona. It's in the vicinity of Chinle, Arizona. So it's a bit to the east of where Grand Canyon is. And that foot track, as you can see, it's only about an inch or so long. So that mustn't have been a very large dinosaur. In fact, it was a dinosaur that was probably about the size of a large chicken or maybe a small turkey. But it left behind that 3-toe track. Now, this is not the actual track. This is a plaster cast of that track because the original track is actually preserved in the Smithsonian Institution. It's too precious because this is one of the first dinosaurs that ever occupied North America and Arizona. It appeared about 225 million years ago. Okay, this was again, you don't find these rocks at Grand Canyon, but you do find them in other parts of Arizona, not too far away from Grand Canyon. And I couldn't get away without showing you at least one dinosaur fossil, right? So we had to see that at least once. All right. So without uplift, there would be no Grand Canyon. And I'm just going to finish by saying that again, if I leave you with nothing else today, I'd like you to remember that the Grand Canyon is geologically young. The evidence is that it's about only 6 million years old. But the rocks it cuts through are far, far older. They're thousands of times older than the Grand Canyon is itself. So we have old rocks and young canyon. And so again, I'd like to encourage you to learn more about rocks, and Justin's going to give you some great references as to how you can learn more. And do visit Grand Canyon. If you haven't already, you definitely need to go there. If you've been, it's always worth going back again. And I'll just say thanks very much, and I'll turn it back over to Rick.
Hey, thank you, Steve. Thank you very, very much. And so I talk to people all the time that say they haven't been to the Grand Canyon yet, and so you can live here and it's always going to be there. It's always been there. And people tend to say, "Oh, I'll just do it later, and I'll do it later." But I'm going to, like you, encourage people just to go up there, just experience that, and because it's worth many, many visits, and uh, and the Trail of Time is really an amazing project, and so you should be very proud of that. I'm going to invite our students to kind of just see if if they can glean any questions from the audience for you based on the talk, and then we have a little poll coming up, and then I'm going to get back to you. I want to ask you about some Phoenix rock, some stuff that I found in my neighborhood. So students, what do you have?
Thank you, Rick. We're first going to start out with a poll, and while we have people answer that, we're going to do answer some live questions if we have them. So the first, I'm going to launch this poll question. The oldest rocks at the Grand Canyon are how old? And while the audience answers that,
Hey, I
Spoo,
just
do you have
heard this.
questions for him?
Yep. So Terence asks what type of rock are fossils found in. So I think Dr. Semken already addressed it. Sedimentary rocks, they over time they are compacted and cemented into sedimentary rocks, and those are the type of rocks that you find fossils in. This one's for Dr. Semken, which would be Joanne asks, what books or guides would you recommend to read about the local Phoenix and surrounding area geology?
That's a great question.
Good question. Yeah.
It's a very good question. The first thing I would say is actually one of the best sources for current information is actually on the web, and that's the website of the Arizona Geological Survey. Okay, which I think that Justin is going to show that link hopefully with the Arizona Geological Survey, and they actually have a Facebook page and they have a blog where they tell you information. It's a great way to catch up. But as far as books go, Okay, there's a book that's been out for a while. It's called Roadside Geology of Arizona, and the current version, I have to say, is a little bit out of date. Okay, it was published many years ago, but I'm very pleased to say that ASU's own Professor Steve Reynolds, who is a great Arizona geologist, is in the process of revising that book, and it's supposed to come out, I think, sometime next year. So there's a book called Roadside Geology of Arizona, and the one that's out now is okay, but the one the new version is going to be much better. Now there's another really good book that's called Ancient Landscapes of the Colorado Plateau, and that's a book that was written by Dr. Ronald Blakey, who made those cool maps of what Arizona used to look like, and Wayne Ranney, who's a great Grand Canyon geologist, and that's called Ancient Landscapes of the Colorado Plateau. And that talks mostly about the geology of northern Arizona, but it's a wonderful reference with amazing illustrations, just incredible colored geologic illustrations. So I highly recommend that one as well.
Awesome.
Good. Well,
Also, let's just launch a second poll, and Justin would like to take another question. So we go ahead and stop the polls, and then Alex, do you want to do that?
Yeah. So real quickly, just 1750 million years. That's the correct answer. Everyone got it right. Majority of you. Good job. And then
that means they're listening. They're learning.
means they're listening. And then the other
that's
question is, what types of rocks can you find in the Grand Canyon?
So go ahead and cast your votes while Justin takes another question.
The picture behind me is a hint.
Yes, it is. Actually, Steve, while they're doing this, while you were doing your thing and you're reaching behind you to get rocks, I don't know if you know this, but it looks like you're reaching into the Grand Canyon and just like pulling them right out of. I think it's really cool. I don't know if you meant to do that, but it was
I think that was unintentional, but that's where they all, I've got to admit, most of them didn't actually come from the Grand Canyon itself, because the Grand Canyon is a national park, and you're not supposed to collect rocks in national park. But
that's right. You could get in trouble for that.
But there are very similar rocks outside the park if you know where to look. That the same kind of rocks that are found in the park are exposed outside the park too, and that's where we collect it. So
sounds good.
Yes, if you have a permit, you can get a permit to collect, and if you're going to do research, scientific research. But no, please do not collect rocks in national parks. That's
not in the park itself. No,
not a good thing to do.
All right.
Okay.
Everybody got that one right.
Yeah, basically everyone got this right. All of the above. That's correct. So good job, everybody.
That's absolutely correct.
And I think that's all we have for our break.
So here's the next thing I wanted to do is 2 weeks ago I played a really quick little movie. It was me and my dog out in the park, and Alex is just going to play it for you real quick. And then what I'm going to do is ask Steve to help us identify some rocks. So if you watched 2 weeks ago, you saw this. If you didn't, then this is kind of the setup for this part of the program. Here you go.
Hi everyone. Luna and I are in the Phoenix Mountain Preserve near Piestewa Peak. We like to use this place as one of our regular running spots. Luna likes it because she finds bunnies out here. I like it because there's a little piece of nature near my house that I can enjoy on my morning runs. If you look down that way, down the trail, there's a Phoenix park named Granada Park. There's a lake there, lots of ducks for Luna to bark at. If you look up in the other direction, that's Piestewa Peak. In 2 weeks, we're going to be celebrating Earth Day, and our guest at our virtual night sky program will be Dr. Steve Semken from the Arizona State University School of Earth and Space Exploration. Steve is going to be presenting to us about geology in Arizona. Luna and I are out here looking for a couple of rocks. We're going to ask Steve to identify them and learn what they tell us about the origin of Piestewa Peak, and then maybe something about the geology of the Phoenix metro area. Okay, here's the rocks we found. Let's see what Steve has to say about them.
Excellent. I'm going to share my screen now because I have a little some of those rocks to show Steve. See if I can get to that. So these are the three that you saw that Luna and I found, and I have close-ups of these. So I'm going to start with the left one is kind of a grayish color and a little bit better detail in that. So Steve, what do you think? What do we got going here?
Well, I'm gonna start by saying that one of the cool things about Phoenix is that Phoenix is at low elevation, right? The Grand Canyon is high. The Colorado Plateau, which is where the Grand Canyon is high in elevation, but the Grand Canyon cuts deeply down into it, right? So it exposes rocks that are at great depth. But in southern Arizona, what has happened is that geological processes have basically removed a lot of the same overlying rocks that we have at Grand Canyon, the sedimentary rocks, those big layers. They used to be present down here, but they're gone now. And so when you drive around Phoenix and you go to places like Piestewa Peak, you're actually looking at much the same kind of metamorphic and igneous rocks that you see at the very bottom of Grand Canyon. So that's kind of exciting to think that's similar, not the exact same rocks, but similar rocks and rocks that are about the same age are right there at the surface in Phoenix. And so the rock on the left is what's called a phyllite. It's a metamorphic rock. It's kind of like the schist that I showed you. The only difference is that the grains in it, the crystals in it, are a little bit smaller. But if you look at the middle picture there,
actually, yeah, these are two images of the same rock.
Right.
So
if you look at the middle picture there, you can kind of see those where those grains are kind of lined up in parallel layers. Can you see that? There's kind of it's not very well shown. The picture on the left, you can actually see where the rock is peeling away along those layers. So that's a metamorphic rock. That's definitely a metamorphic rock.
Okay, we got another little sample here. This is real quickly. We're running out of time, but go ahead.
This is another metamorphic rock, but we call this a quartzite. And this is a rock that's basically started out as sandstone, which was a sedimentary rock, and it got squeezed and heated up, and all those sand grains kind of fused together to make this kind of a purplish red rock. And the color purple is probably just due to the way that the light actually interacts with the quartz in the rock, and white light comes in and purple light comes out, basically.
You said earlier about a rock hammer to chop it out. Now, I didn't break this rock. It's just sort of where I find them. It just they're already sort of like, kind of broken up and all that kind of stuff.
Well, you notice the surface on the left is kind of weathered. So but the surface you're holding there is the fresh surface, and that's why we use hammers, because that tells us what the rock really looks like.
Here you go. And here's the last one.
Now that one is very interesting. That's basically a big lump of rock that's made out of the mineral quartz. We call that a quartz vein. And what that is that's a piece of a crack that was actually in those metamorphic rocks, and hot water probably is what it was, is percolated through those back at the time when those mountains were being built and all that land was being smushed together. And it left behind sort of like a little film of quartz. And then later on, that film just kind of came loose and broke out in pieces. So that's what we call a quartz vein. And what's cool about those is that in some places, those quartz veins will have precious metals in them. They'll have gold and silver in them. But don't go looking for gold and silver in Piestewa Peak, because you're not going to find any.
Find it there. Okay, last question for you, and this is kind of important to me. I'm thinking about Luna's future. Do you think she has a future as a rock hound?
Oh, all dogs make great rock hounds, and I'll give a shout out to my own rock hound Dulce, who's watching right now. But Luna too. All dogs make great rock hounds.
Excellent. Okay, I am going to take a moment, and so just to tell the audience, we're just running a little long, and we think it's okay. So we're just going to we're going to go past our hour time frame here, and so hang with us as long as you can, please. We've got just a couple more things to show you, and an upcoming update on the Ingenuity flight, the helicopter on Mars. But before we get there, I want to introduce Justin Baez. Justin has been a docent in our program for a long time, and he's quite a spirit around our place. We just love having him. He comes to us from a geology background. He loves paleontology, and we asked him just to give you a demonstration of some resources you can just find on your computer and how to use it to just know a little bit more about Earth geology. So Justin, take over, please. Do I have to stop share? Oops.
Yes, you need to stop sharing.
I don't want to stop sharing. Okay, got it.
Cool. Hey everyone, my name is Justin. You can call me a friendly neighborhood geologist because I love geology. So right here, what we're looking at is Google Earth. Google Earth is a compilation of many images of the Earth, and it's pretty much a good way of getting familiar with what's out there. Something that I use Google Earth for is for my own research. You know, Google Earth has information about Arizona. It has information about anywhere you can think of that's on the Earth, and it's very informative to what kind of processes are actually going about that either act on its own or act on its own, but has another consequence by affecting another process. You know, these continents, you can see the scar from when Pangea Earth 220 million years ago split apart. And I encourage you guys to look at Google Earth, download it, and ask questions about why we see the things we see. You know, geology is different from astronomy, like the other previous virtual sky nights, is because, you know, we can actually go out in our backyards and explore the world. And I really encourage you guys to kind of just check it out and let us know what you think. So yeah.
Thank you. Thank you. Oh, go ahead.
No, I wasn't curious. I wasn't sure whether I should go on with other things or you guys can go to Alicia.
Yeah, I think, thank you. And one of the reasons to bring this up, and thank you for showing us, Justin, is that there are so many resources now for young people and people online. Google Earth is free. And so you can just go and just kind of explore. And I guess we challenge you to go to Google Earth, look around and just see, just kind of look with the eye for geological features, things that are happening that you could look into and just get a little bit, you know, kind of dig a little deeper and get an explanation for why they're that. And so thanks, Justin. I'm going to switch gears and let's move to Alicia because some really amazing event happened on Mars this week. And Alicia will give you a little sense of what that is.
Thank you so much, Rick. And thank you to Justin for sharing our resource of the week. It goes perfectly because what we're going to talk about is Ingenuity, and Ingenuity is a helicopter that we have on Mars. And that's this week's current event. And so I'm going to talk to you a little bit about that. So Perseverance is a rover on Mars. Is our 2020 rover, and it launched a while ago and just recently arrived on Mars in February. And so Ingenuity is a little helicopter aircraft that was attached or was on board the spacecraft and is now functional. And so here we have Ingenuity and Perseverance taking a selfie using the Watson camera. And this is a selfie that was taken at about a 13-foot distance apart. So even they were social distancing on the red planet. And here we have Ingenuity up and close. This was a photo that was done by the cameras aboard the aboard the Perseverance rover. And those were the Mastcam Z cameras that we built here at Arizona State University. So not only, sorry, let me go back really quick. It looks like my GIF isn't loading. Not only did that image show that Ingenuity survived its first night on the Martian surface, its first cold night on the Martian surface, but this GIF was supposed to represent its successful test and propeller maneuver. And so it did have a successful test. And so this image is from all the brilliant people, all the brilliant minds at work trying to get Ingenuity to work and to fly for its first test, which was done on Monday, April 19th. And so it was successful, as you can tell by the cheering on the top left image. And it looks very familiar to the happiness that we saw at at ISTB4 on ASU's campus when we found out that Perseverance had landed safely on Mars. So again, it was kind of, it was a very joyous occasion knowing that Ingenuity was successful. And so here Ingenuity is hovering above the Martian surface, and it actually took its own photo. It took this photo, the first black and white photo to ever be taken by a helicopter or aircraft on another planet. And so Ingenuity took this black and white photo using its navigation cam. And this camera is really neat because it will it will follow where Ingenuity goes, and it will track the ground beneath it. And so, whoops, there we go. What's really neat, not only are there cameras on board the Ingenuity helicopter so it can take images, but also we can use the cameras on board of the on board the Perseverance rover to watch Ingenuity. So here we are looking at its flight and watching its first controlled flight that happened, like I said, Monday, April 19th. And so we're getting great images back, and we're going to follow it along its journey. So please stick around for current events to hear more about this. And with that being said, I'm going to pass things back over to Rick to wrap up the rest of our show.
Thank you. Thanks, Alicia. We can always kind of count on you for a good, concise report on those things. I also was with Professor Jim Bell today, and they are preparing for the second flight tomorrow morning. So I think by the time we get up and start heading for work and start getting on with our day, check out sort of the latest feeds, because I believe we're going to see flight number 2. That particular flight you saw, they just went up 3 meters, about 10 feet. Hovered for a little while, came straight back down. Let's see what paces they put the Ingenuity through tomorrow as we go. I think that'll be great. Okay, I wanted to just say there's some upcoming events. First of all, tomorrow is Earth Day, and we have a New Discoveries lecture series lecture. This is something that we do live in the theater and have been doing for about 5 or 6 years. Many audiences come and see these are scientific lectures about certain subjects and things like that. So of course, we're virtual now. We're not live yet. We will be soon enough. But the lecture tomorrow night in celebration of Earth Day is called Earth Innovation. It's a collaborative science and engineering for exploring desert ecosystems. And Professors Troop and Dawes will be co-presenting tomorrow night, and they're bringing the science perspective, the engineering perspective, and they're looking specifically at desert ecosystems as they do that. So please look that up if you wanna take advantage of that. I think it would be amazing, and I hope you like that. Next week, let me see if I can do a quick little share again. I wanted to, or it was in 2 weeks on May the 5th, Cinco de Mayo, we will be actually back with you on a Wednesday night, and we are back in space. We will be working, there's my dog, we'll be actually sort of like redoing this concept we started about sort of learning how the sky works and all that stuff. Remember 2 weeks ago, we looked at stars, we looked at seasonality, we looked at how things change over hours and over seasons, and how you can use the sky to map what's going on. We are going to kind of switch our gears to planets. And if you remember in Steve's presentation at the very beginning, he was talking about planets, and the things that we have in common with the planets of the inner solar system is that we are all terrestrial. There is a surface. And so it just so happens this is a view of May the 5th, and it's just after sunset. You can see the sun has just gone below the horizon, and you see above it is Venus, Mercury, and Mars, all of the inner planets that share our part of space, and all of them will be visible. We're going to take a little look at how to look for them, how to find Mercury, because it's hard, what's happening with Mars and where it's going. And then we're going to welcome Venus to the night sky, because once you can start seeing it, hopefully on the 5th, but the 6th and the 7th, once you start seeing it, it's visible every evening for about 270, 275 days. And so it will be part of our night sky, and we'll welcome it. We also will be saying goodbye to that really special group of stars that we've been watching since December, all of the bright stars about Orion and Sirius and the twins and Elijah. They will be melting into the sky very, very soon. So we'll lose them as stars, but we'll kind of start concentrating on these inner rocky planets in 2 weeks. So thank you very, very much for joining us tonight. We appreciate every time you come. You will get a survey from Kim in the next day or so, and please make comments about what you saw, things that you might want to see. And if you have any other questions, please ask them, because we will we'll follow up with answers as soon as we can. But keep tuning in. So So every other week we continue. We'll do this all the way through the summer. We have plans, and we appreciate the audience that has stuck with us for all these years. So thank you for joining us tonight for our version of the night sky. In this case, geology, and special thanks to Steve Semken, Professor Semken, and his presentation about Arizona geology. So I appreciate it, Steve. Thank you, everybody. Enjoy.